Please give a warm Texas welcome to Elon Musk.
All right, thank you for having me here. Appreciate the invitation, and I suspect I'll be visiting Houston quite frequently in the future, given the cost contract. So we've got a great city, and I always look forward to visiting. So we'll talk about SpaceX, give you a little bit of background, tell you about the last launch that we had, and then tell you about where things are going long term, and at least try to leave some time for questions, because I find that's often the best part of any presentation. Allows me to interact and really address anything you're curious about. So SpaceX was founded about 5 years ago. The long-term goal was to really dramatically improve the cost and the reliability of space transportation. It doesn't help if you just improve the cost, but the reliability suffers. So reliability is, in fact, has been our primary focus, and cost secondary. The initial market was small government commercial satellites with the Falcon 1. And the idea behind the Falcon 1 was that it would serve as a scale model, as something where we could test out the technologies, and when we make mistakes, they're made at a smaller scale, rather than jump immediately to a large rocket and make mistakes which cost 10 times as much. So that's a strategy we've been executing, and I think it's worked out reasonably well so far. But it's worth noting that the plan for SpaceX from the very beginning was always human transportation. So can we really make some progress in helping humanity become a true space-faring civilization, where a large number of people can afford to go to space, and where it's not limited to just a really small number of people every year. So if we can help set space transportation on a path of continuous improvement in cost and reliability, as we saw with aviation, the early days of aviation were extremely risky, extremely expensive, but over time that improved, and to the point where today you can buy a nonstop flight from Houston to London for the return ticket for $500. I mean, that didn't even used to be possible, and then even when it was possible initially, it used to cost 10 times that amount, and now it's very affordable. So that was brought about by there being constant improvement in aviation over time. And so if we can help make that happen, then I'll consider SpaceX to be successful. If all we do is be yet another satellite launcher or something like that, or ultimately are only about as good as Soyuz in cost per person to orbit, I mean, that would be okay, but really not a success in my book. So anyway, the long-term holy grail is can SpaceX help establish a permanent presence beyond Earth? Personally, I think if humanity can help establish life on another planet and extend life, make it multi-planetary, I think that really would be one of the most important things that we could possibly achieve. If you think about the important milestones in the history of life itself, and that means going beyond the parochial concerns of humanity. Initially there was single-celled life, and then there was multicellular life, and then things acquired skeletons, and then some of those things transitioned from the ocean to land. You had the development of mammals, and there's probably about 10 or 12 really big milestones in the history of life itself. And I think on that same scale would fit life becoming multiplanetary. I think it would be at least as important as life going from the oceans to land, and arguably more important. To the best of our knowledge, life exists only on Earth, so if we don't at some point propagate beyond Earth, then there will be some calamity that befalls life here that will extinguish it. And for all we know, that may be the extinguishment of life itself. So I think it's really important that we try to do this, and if humanity is one day able to do this, it will require really orders of magnitude reduction in the cost of space transportation, and much more reliable space transportation as well. So SpaceX operates on a Silicon Valley type of mode of operation. It's a flat hierarchy, close-packed cubes, high engineered to manager ratio, rapid prototype iteration, and could operate on a best idea wins type of philosophy, where what matters is the merits of the argument, not the arguer, not the status of the arguer. So we started with 3 people 5 years ago. We're now over 300, and I think we'll probably be over 400 within 12 months. So we're growing pretty quickly. We're currently 100,000 square feet of office and manufacturing space in near LAX, about 2 miles south of LAX, and we're expanding to 500,000 square feet later this year. We have a big propulsion structural test facility here in Texas, just halfway between Austin and Dallas. If you want to hear, there's a little town called McGregor. That's where our test facility is. And then we've got launch complexes in Kwajalein. Kwajalein is currently our primary launch facility. We have a dormant facility at Vandenberg, and you may have read that we recently were awarded Launch Pad 40 at Cape Canaveral, which is a great launch pad. It was used to launch the Titan IV heavy lift vehicle until about a year ago. So this is what our first building looked like 5 years ago. This is what the building looks like that we're moving to later this year. That gigantic thing there. The ceiling height is about 60 feet. That was used to build 747 fuselages until last year. These are some pictures of our Texas test facilities. So we have a number of propulsion test stands and structural test stands. These are Falcon 9 test stands. So the one on the left is where we'll be doing the stage hold down firings of Falcon 9. So as you can see, a very, very big stand. And the top of the concrete is about 130 feet. And then what we call the stairway to heaven, which is this narrow stairwell, it goes up about another 100 feet. It's the tallest thing for, I don't know, 20 or 30 miles. So we have to put an FAA beacon on top so planes don't fly into it. And there's a construction elevator along the one leg, and then the plumbing goes up the other leg. And on the right-hand side is the structural test stand for the Falcon 9 thrust frame. So that is what takes the 9 engines of the Falcon 9, and those hydraulics are capable of pushing down with about 1.5 million pounds of force. So it's a very stout structure. Here's take note that the SpaceX track record to date, which I think is a good predictor of future performance. The Falcon 1 was really developed from a clean sheet to being on the launch pad in 3 years. And that includes the entire vehicle. So the entire vehicle was designed, built, and tested at SpaceX almost. I mean, there were a few pieces that were procured outside, but we have a very high mass fraction first stage. It's a 94.5% propellant mass fraction first stage. There's about 0.2% residuals included in that, which I think may be the highest mass fraction first stage in the world currently. I think the previous record was held by the Titan II first stage. And that includes a recovery system, so there's a parachute system included there. The upper stage is pressure fed, both the fairing, stage and fairing separation systems. It's worth noting that the Merlin 1A engine, the main engine on Falcon 1, is only the second American pump-jet booster engine to see flight in about 25 years. The other one was the RS-68 for Delta IV, and before that it was the Space Shuttle main engine. It's actually the first new American hydrocarbon engine to see flight in, I think, since the 60s. So, and then there's also Kestrel, which is the upper stage engine that we developed. That's a pressure-fed engine, restartable, pretty good ISP, and we've got a low-cost avionics system, which has the advantage of, since this is designed in the 21st century, of being a 21st century, of using 21st century electronics for the guidance and control. The Falcon 1 is the first non-explosive orbital flight termination system approved by range safety. So we actually don't, the rocket, when the range safety officer presses the stop button, it just shuts off the engine, so it actually doesn't explode the rocket. We initially set up at Vandenberg, and then were forced to move to Kwajalein. So we did 2 launch sites and control centers. And so we're at the price, we started out at a price of roughly $7 million 4 years ago, and we've kept that price constant, which is actually a decline when you take inflation into account. So this is 2 years after starting the company. We have the qualification article of Falcon 1 on the launch pad at Vandenberg. And then about 6 months later, we did the static fire. So we have sound, but I guess it's not working for some reason. So unfortunately, we were forced to move from Vandenberg to Kwajalein, and so we moved from May of 2005 to November 2005. We were able to set up a launch facility at Kwajalein, which is quite difficult because the island we were given in the Kwajalein atoll was just had nothing on it. It was just jungle. So we had to bring in power, water, RP. Not kerosene, all the pressure rates, offices, that sort of thing. And we definitely had some challenges with liquid oxygen in particular, since Kwajalein is 5,000 miles away from California and about over 2,000 miles away from Hawaii, which is the nearest source of liquid oxygen. But we managed to get to our first countdown right on Thanksgiving 2005 at Turkey on the Island. So it took us 4 countdowns to get to the first test flight, which was in March of 2006. So I need to edit this video because it's like 60 seconds worth of precursor. But yeah, so I think it's worth seeing this timeline because a lot of people don't realize that we actually had the vehicle designed, built, and ready to go 3 years after starting the company. And unfortunately, the launch site issues caused us to delay by another year, effectively. This flight, hopefully the thing will take off any minute now. But unfortunately, the sad thing is that the issue that caused the problem with the first flight was a corrosion issue due to the Kwaj climate. So there's some probability that would have occurred if they had launched out of Vandenberg. But unfortunately, it came back later. So the telemetry basically showed that there was a kerosene leak at the turbo pump inlet pressure transducer, which started about 400 seconds prior to liftoff. You couldn't see it because the wind was blowing, and kerosene is actually vertical to sea. So when the wind's blowing, you can't actually see that it's leaking. The failure review board, which was actually co-chaired by Pete Warden, who's one of Ames, concluded that was due to corrosion, stress corrosion cracking of the aluminum B-nut on the engine. That leak ignited a few seconds prior to start, and the power basically burned through the entire powered flight. And about 25 seconds into the flight, it burned through a helium pneumatic line, resulting in loss of helium pressure, and that caused the propellant pre-valves to shut and essentially turning off the engine. Other than that, everything looked good. The vehicle was proceeding along its design trajectory within 0.2 degrees. All first-stage systems were nominal, and all avionics were nominal. So we took a bunch of corrective actions. We improved the vehicle robustness by eliminating as many fittings as possible and going to orbital tube welds, by replacing aluminum fittings with stainless steel at a slight mass penalty. Actually, the stainless fittings cost less than the aluminum fittings, so this was a cost savings, I suppose. A number of other changes. We also added more detailed procedures, some more personnel to the process. So a triple sign-off was required by all on all work, both the technician, the responsible engineer, and an independent QA person were required to sign up on all work on flight hardware. And then close out photos. And we also went through ISO 9001 certification last year. The biggest single change is we massively improved the software health monitoring and launch automation. We were monitoring approximately 30 variables. We went to monitoring 800, including both the vehicle and the ground support equipment. And we would have caught the fuel leak if we had the system in place. And the countdown is also now fully automated, which reduces the potential for human error and allows engineers to focus on the data. It also allows us to take some number of personnel out of the countdown process, people that were just basically doing the job that the computer was doing. So although we added people on the QA side of things, we were able to reduce people on the launch ops side by having increased automation. So ISO certificate. So as far as Demo Flight 2, which took place in March, we just finished the post-flight review with our customer that shows that the only orbit critical issue was lack of slosh baffles in the second stage, the LOX tank, that caused decoupling of the control and slosh modes. We did obtain full telemetry and video well past nominal end of mission. There were actually 3 dishes following the vehicle, and although some dishes, fortunately, at any given point there was 1 dish with a good signal. So we were able to splice together the telemetry and video to get a full mission duration. So all systems and flight regimes were tested, demonstrated a highly responsive launch. If you were following it closely, so we were able to light the engine, abort, detank, retank, and launch in 70 minutes. It was considered a success as a test flight by DARPA and by SpaceX. And we will be launching our first 2 operational satellites later this year. The first will be TACSAT for Navy Research Lab, and the second will be in October, and then the second will be a Malaysian Space Agency satellite in December. We have a total of 5 Falcon 1 missions and 6 Falcon 9 missions on our upcoming schedule, and we expect to close probably 4 more Falcon 1 and 3 more Falcon 9 missions in the next, through the balance of this year. And that will bring us to 20 launch contracts in total, including the 2 that have taken place. So Falcon 9, and there's information on our website if anyone's curious as well, but it's designed to NASA safety margins, mandating safety margins of failure tolerance. It's roughly 840 pounds of thrust, 840,000 pounds of thrust at liftoff, with a maximum mass of about 700,000 pounds. So, sort of on the order of the Soyuz in size. 12-foot main body diameter, rising 17-foot with the large fairing. I actually don't have a picture of the vehicle with the large fairing, but it's kind of the big fairing you'd see on, say, an Atlas V or a Duffel. And the vehicle is 150 foot with Dragon, 180 with the large fairing. The 9 engines on the first stage are being carefully designed to provide engine out capability. So if we lose an engine, you can still complete your mission successfully. And depending upon the phase of flight, you could actually lose multiple engines and still complete the mission. And basically, it's a sort of a 10-ton to orbit type of vehicle. Some people are worried about the number of engines, but I think it's worth seeing pictures of what the Soyuz looks like on the base end. There's quite a few thrust chambers there. The Russians have a definition of engine where they only count things by the number of turbo pumps, but that's kind of a silly definition because by that definition, the Falcon 1 doesn't have an upper stage engine. So I think you really need to count it by the number of thrust chambers. So each thrust chamber is an engine. So Soyuz has 32 engines on the base. Saturn 1 has or had 8 engines on the base, but those each have an individual turbo pump. So Falcon 9 is really quite comparable to Saturn 1B. It's got one extra engine, basically. So the basic concept of operations for Falcon 9 with the Dragon spacecraft is real simple. It's a 2-stage vehicle. So the Falcon 9 drops the Dragon off in orbit, and then Dragon goes from that parking orbit, maneuvers under its own power to the space station, where it's captured by the arm and berthed to the station. And then re-enters, the same way that the Apollo capsules re-entered, full body re-entry, lands in the ocean. Although we have the ability to have it land on land as well. We're just starting off with the ocean because it's easier to get the regulatory approvals, and the Earth is mostly ocean. So if you need to get down in a hurry, you better be prepared to land in the ocean. So as far as Falcon 9 itself, we finished serial number 1 of the first stage primary structure, which ships to I think I mentioned this, shipping up to Texas, to our Texas testing site in a few weeks. We'll be starting the first flight unit, serial number 2, in 3 weeks. It's made of aluminum lithium in the barrel sections and 2219, sort of a standard aluminum in the domes. This year we'll probably produce, I think, 2 flight units, and next year we'll be producing probably 6. The year after that, as much as 12. It really depends on what the demand is. We have achieved our 1C development goals and actually exceeded them slightly. The goals were 92,000 pounds of sea level thrust and 299 vacuum ISP. We've gotten to 94,000 pounds of thrust at sea level and clear to vacuum ISP for a full mission duty cycle. And we expect to finish qualification of the Merlin 1C in July. We have tooling and material in place for 25 of the engines this year, at 40 or so next year. We'll start doing integrated stage and engine testing in August, most likely. And there's going to be a progression of multi-engine firings, starting with 1, 3, 5, and then probably 9. And we'll do a full stage roll-down acceptance test of the first flight stage before we send it to the launch pad. Actually, like this. So this is the Merlin 1C, just a recent firing of the Merlin 1C. Goes on for a while. so you can get it. Actually, I'll pause it here. So there you can see the whole engines in the stand there. The chamber is milled copper liner with a nickel cobalt electroplated nickel cobalt closeout. The nozzle is a brazed tubal nozzle. So it's actually an architecture similar to the SSME, but way less expensive in terms of the way it's made. So the Miller 1C is designed for a man rating, so it's got a 50% margin above flight loads. And it's actually more than what's needed for man rating. It's also fortified against foreign object ingestion, and we'll be doing foreign object, and have done actually inadvertently some foreign object tests. And so far it's held up quite well. But we'll be doing a formal set of foreign ingestion tests to verify that maybe if it gets reflects on a piece of aluminum or steel or some organic or something like that, that it doesn't cause the engine to come apart. And we want to try to reach 25 or more cycles before any refurbishment, and ideally something on the order of 100 cycles before the primary elements need to be replaced. The turbopump assembly is about as simple as you can have a turbopump system. It's a single shaft with 2 pumps on it. So they'll start up at the same time by definition. It uses a Pentel injector, which is insensitive to contamination, no known combustion instability issues. And I talked a little bit about the chamber nozzle. We will be having Kevlar flak jacketing between the engines of the Falcon 9, so even if an engine does come apart explosively or in a fire, it will be protected against damaging any of its neighbors. Oh, it's worth noting that SpaceX will produce more booster engines this year than any country except Russia. So we'll be producing about a total of 30 engines, roughly 5 Kestrel engines and 25 Merlin engines. And I think that's more than any country in Russia, except Russia. Certainly more than the rest of U.S. production combined. It's a picture of the Falcon 9 first stage primary structure. We're a little cramped in our current building. It only just gets out by a few inches. As far as the second stage, one of the ways in which we've designed Falcon 9 to be fundamentally lower cost is that the second stage is simply a shortened version of the first stage. So it's the same dome, same material, same tooling, same manufacturing line, which may seem like a pretty obvious move, but as far as I know, there's no rocket out there that takes this approach. Each stage is designed like a unique spacecraft. So it really takes us almost no time to make the second stage, because it's really just 2 barrel sections and 3 domes. So we should finish the first unit in 5 months, and no problem doing sort of 1 every 2 months by next year. It will have a Merlin 1C vacuum version as the engine. So same engine that you saw there, but with a vacuum skirt extension. It's a big valve nozzle. The avionics guidance control, there's quite a lot of heritage from Falcon 1. Interior, we could fly the Falcon 1 avionics, and apart from some changes to the software, it would work. But we'll be upgrading this to be triple redundant voting to meet NASA man rating standards. We're also going to add multi-engine controls at the first stage, obviously, and we'll be upgrading the avionics to higher radiation tolerance for missions that are long duration or pass beyond the Van Allen belts. And then the fairing, all the fairing tooling is done. We should have our first production quarter section in a few months, and have the full fairing in about 6 months. So as far as Dragon is concerned, looks like all things are good for demo and CDR in August. The basic structure is an isogrid aluminum pressure vessel with aluminum lithium for the primary road path elements. The nose cone and heat shield support structure of carbon fiber composite. We finished a structural / manufacturing test unit earlier this year, which was made in using the same methods and same materials as the flight unit, and all materials are ordered for the flight unit. The propulsion system of Dragon will use 18 SpaceX Draco engines. Draco means little dragon. They're roughly 90 pounds of thrust each, using nitrogen oxide and monomethyl hydrazine, and will be used in continuous mode for orbit changes and 10 millisecond pulse mode for attitude control. So it's sort of a fairly unique engine, and pretty advanced. Uses a space shuttle principle to achieve extremely fine pulse mode capability. And then from a thermal standpoint, it's designed to run continuously. So let's see. We'll be using titanium propellant tanks with the propellant management device and a composite helium tanks from RDA, and we'll start testing the engines this summer. The heat shield, we've changed to Pika as the primary material, which I told you guys. So Pika is a phenolic impregnated carbon ablator. We decided to switch to that because it is fully octet tested, so it's qualified from an octet standpoint. And we have updated version of SLA 561 as backup. That's pretty technical stuff, so probably a lot of people don't know what that means, but basically the brake pad. So we will actually be using the SLA material on the Falcon 9 second stage. So the Falcon 9, I have to mention that the Falcon 9 is designed to be reusable as well as Dragon. So the Falcon 9 second stage needs a heat shield in order to be able to re-enter and survive. And the heat shield we'll be using on that is actually an SLA heat shield. But we do not plan on octet testing that, because recovery of the Falcon 9 booster is an optional thing. It's not required. So we feel confident enough to actually fly the second stage re-entry with SLA that hasn't been octet tested. And if it works, great. If it doesn't work, well, nothing will. And then parachutes, we're working with the Irvin. There'll be 3 main ring sails and 2 drogues, so you can lose either a main. We can lose a main and you can lose a drogue, and things are still okay. Very low normal descent rate of 20 feet per second, which is about what a parachutist would come down at. And that allows us to transition from the ocean to land pretty easily. So on the left there is the structural test unit that I mentioned. You can see the machined isogoot door. And although the first missions for Dragon are cargo, we're designing everything for manned loads. So it's designed to take the loads of an escape rocket and to take high G aborts and all that stuff. And it's also got windows, which cargo does not need. And then on the right, you can see what it looks like with the engines when the engines are on. So the left is like kind of cargo configuration. On the base of Dragon, the sleeve that connects Dragon to the booster, we use that to carry unpressurized cargo, and also it'll contain the solar and the radiator. And on the right, you can see in the crew configuration. So we're designing it to have a maximum of 7 crew with there'll be a small seat and a big seat. So 4 small seats and 3 big seats. And then you can see the common berthing mechanism. That interface at the top is where it'll berth to the space station. So the nose cone gets tossed away, and then it berths to the space station on that interface. A few more pictures of it. You can see it stuck on a little section of the space station. And that's it. And there's actually also more videos and pictures and whatnot that you can see on the SpaceX website. I should also say, where do I see the future of commercial spaceflight? Well, I think we're really entering a new era that's very exciting for commercial spaceflight. There's a lot of things happening on the suborbital front. with Jeff Bezos and Blue Origin. You've got obviously Burt Rutan, Scale Composites, and Virgin Galactic. And we've got John Carmack, who's here in Texas with Armadillo Aerospace. I think John's going to do really well. And then on the orbital front, you've got ourselves and Rocket Plane Kistler, and I think we'll see some of the companies that are doing suborbital work transition at some point to orbital activity. So I think it's pretty exciting. If all goes well, SpaceX will be flying and supporting the space station for many years to come, and also potentially supporting things like the Bigelow space station, and who knows, all sorts of other things that will develop. So I'm really bullish on the future of space flight, so I'm really excited about it. Are there any? So the question is it possible to put Orion on top of the Falcon 9 and get it to orbit? Well, it sort of depends on what the mass of Orion is considered to be. So I think if it was, the capability of the basic Falcon 9 is 10 tons to LEO. So, but there is a heavy version of Falcon 9 that we'll be developing with the side boosters, which is similar to the Delta IV Heavy, the common booster flow approach. I believe that may be able to put Orion into orbit, because that's capabilities on the order of 25 metric tons. So it's just, I think within our possibility. Well, actually, I didn't do any market research. So maybe that's why I did it. If I had done market research, I would have probably not done it. So no, I do think there's a market for what we're building. I didn't do any market research. I certainly read about what rockets exist in the world, what are they launching, and that kind of thing. So I knew that at a minimum we should be able to go and compete in the existing market and have some kind of a business, even if it wasn't really breakthrough or anything like that. So yeah, I mean, there's I don't think there's any kind of market research you could do that would say, okay, if you really believe it, if you can reduce cost by this amount, then there'll be this extra number of launches that occur as a result of that reduced price. I think you just have to do it and hope it turns out to be true, and then make sure that there's a backup plan that you at least have built some value, even if you don't achieve the full potential that you've still got some valuable enterprise that's capable of at least serving the existing market. And that's really the strategy that SpaceX has had. We can at least serve the existing satellite launch market and hopefully the space station. And even if that's all that happens, well, it's not a terrible thing. But hopefully by lowering the costs, improving the reliability, we can expand the market substantially. And I think if we do, there'll be others that enter the market and compete for that business, and just as occurred in the airline business. There was a time when no one could possibly consider aircraft as a transportation mechanism. I mean, there are things that you maybe got a little joyride in, or and they're very dangerous, and lots of people die all the time. And then, if you said in 1920, or probably any time before Lindbergh even asked your average person on the street, do you think you'll be able to fly, from your city to Europe nonstop in an aircraft? They would have said, no way. That's ridiculous. So I think you have to go and approach this with some degree of hope and faith. Yeah, Dragon will be grabbed by the shuttle, by the station arm, with the basic standard grapple fixture. Yeah, it can dock to any CBM port. Well, I'm not entirely certain of any CBM port. I think there's one in particular that we're supposed to dock at, but in theory we could dock at any CBM port. Oh, well, there's multiple videos. We've got 18 cameras, various places, onboard cameras, ground cameras, tracking cameras. So what I showed is just a tiny sampling. There's a lot more on the website, actually. So cost per pound to the space station. Well, I guess initially, I think it's probably like $10,000 a pound. Am I thinking that correctly? Yeah, about that. About $10,000 a pound. And that's cargo to the space station as opposed to cargo to opposed to mass to orbit. The mass to orbit of Falcon 9 is about $1,300 a pound. But that's if you're a satellite or something. So to get stuff to the space station, you need to add drag into the equation, and then you need to basically say, well, that eats up a ton of useful cargo as well. So roughly, approaching 3.5 tons for roughly $70 million ish. Yeah. We have to see how we have our pricing estimates, but we have to see what the final pricing turns out to be. Now, I should point out that assumes zero reusability. So if we are able to make the reusability economics work, that price could be substantially lower. Well, we expect to do probably a lot of commercial flights to geosynchronous orbit. Hopefully some launching some planetary missions, stuff to Mars or Moon or that sort of thing. Okay. See if probably more questions. So it actually is getting harder and harder for me to write blog pieces. I used to write them quite frequently, and now I've got a pretty big family and business things that take up a lot of time, so the blog stuff tends to fall to the bottom of the priority list. And there are a lot of times where I feel really guilty about not updating the blog. But I would like to try to continue to make write blog pieces, and also try to get other people at SpaceX to write blog pieces. At Tesla, a lot of people write blog pieces, so I only write them occasionally. As far as Tesla is concerned, the first production car of the Roadster should be out at the end of summer, so end of September, maybe October. And then Tesla is working hard on a Model 2, which is a $50,000 luxury sports sedan, and that's 4-door, 5-passenger, about the size of the 5 Series BMW, and with a targeted debut at the end of 2009. Oh yeah, Pogo. We have Pogo suppressors on each of the 9 engines, the individual Pogo suppressors. So that should hopefully do the trick. We have a couple of outside experts that are looking at our Pogo suppression devices and helping us design them. The guy Shel Rubin, you may know him if you're familiar with Pogo stuff. And there's a few other people we're bringing on board as well to look at that. But Pogo is certainly something we take seriously. Well, thank you. How about at this point? Biggest risks? I don't know what the biggest risk is, actually. There are lots of risks, but I'm not sure how to order them exactly to say which one is the biggest one. The last demo flight 2, the swash mode coupling with the control frequency of the second stage was number 11 on the dynamic control risk list, number 11. And if you would have merged all the risk lists, I don't know, it would have been number 120. And that's the one that went wrong. So how do it's a very subjective thing to figure out what the real risk is that's going to bite you in the butt. I can't, fortunately, with the knowledge that we'll gain from Falcon 1, and we're not going to make, in retrospect, an elementary error like not having slash baffles on the stage. So I think we'll be safe from that sort of stuff. Yeah, it's possible we could have some challenges getting through the birthing process. I don't know that much about it. It's not an area where I'm all that familiar. We're learning a lot at SpaceX, and we have some outside companies that are very familiar with the process helping us. I think Dave over there from Odyssey. And Harold is helping us with the safety stuff. Well, I wish I could give you a really good. I can't. I don't know. I don't know what the biggest risk is. They're all really big, and it will have to get a lot of attention. Sorry. Actually, I didn't even know it was his 100th anniversary. Good to know. He's written some good books. I like the Newness and Harsh Mistress. That's a good one. We've certainly made some use of existing hardware, such as quick disconnect. In fact, many of the things you mentioned, quick disconnects, regulators, certainly control valves. Most of our control valves are from Murata, which is provides control valves for the shuttle. We use continuum event relief valves. We use Stanford new legs, and a lot of existing satellite componentry in Dragon. The big stuff has been developed from scratch. We kind of have to do that because if we were to cobble together stuff from existing quasi-off-the-shelf components, then we would be unable to reduce the cost, because to the degree that you inherit legacy components, you also, while you may inherit their heritage, of course, you also inherit their cost. And so we were, of necessity, forced to make the major items like the engines and the stages and the avionics and the launch ops and all that, to do that from scratch. Well, I've invested $100 million, approximately. A little more than that. We've spent more than that. So that's sort of invested capital. But we've spent more than that because we've received payments for launch. We did the first 2 Falcon 1 launches. We've received advanced payments on a number of the other launches. We've passed some cost milestones. So I'm not sure exactly. I'd have to think about it. I'd probably consider that proprietary, but we've certainly spent well in excess of $100 million thus far. Although I've only invested roughly $100 million. Yeah, I think it'd be fun to ride in the Dragon at some point. Some people sometimes think that this is a roundabout way of getting me personally into space, but it would be a lot cheaper to buy a ride on the Soyuz. Well, that's asshole. I would definitely like to fly at some point. That'd be great. Yeah, cost has been really helpful in speeding things up. I mean, we wanted to go in that direction long term anyway, but it would have taken us a long time. It would have, we'd have to sort of earn our way there, and also we wouldn't be able to take advantage of the expertise that NASA has, which has been quite helpful in designing a reliable vehicle. So I think the cost program has been really super helpful. It's been great dealing with everyone there, and a lot of people sort of say, well, isn't NASA going to smother you or cause you to do all sorts of inefficient things? And really, that hasn't been the case. I mean, it's with no complaints thus far at all. It's been great. The Vandenberg story is a long and sad story. But yeah, we I don't know, it was unfair, but these things happen. Yeah, actually, the SpaceX manifest is on the website. So if you're curious about the upcoming, which satellites are being launched and who's the customer and when they're being launched, there's actually an updated launch manifest on our website. I think probably, well, for Falcon 1, be under 12 months, maybe 9 months. What we're doing is we're actually buying long lead items ahead of time. So we have an inventory of the long lead stuff. And so once we have long lead stuff in hand, it can take us, for Falcon 1, as little as 9 months to get going and get a launch off. For Falcon 9, well, it's probably a little premature to make claims at this point, but for the booster at least, we do plan on having a continuous production line of the booster, so in theory it should take very little time to get that going, go from a contract to a launch. Hopefully it's 6 months, could be, hopefully 9 months, it could even be 6 months. But it really depends on how the manifest is filling out. There may be other constraints which are not related to SpaceX directly, such as can Cape Canaveral handle that launch, or is there other stuff scheduled for that time frame? They'd really like to see that something scheduled 12 months or even 24 months in advance. So, but we are aiming to have a really short time, ideally, between the contract and launch. And if we're able to make reusability work, then and we have a constant stream of vehicles coming back and getting refurbished and flying, and we're flying every month or even more frequently than that, then it's going to be relatively easy to slot somebody in. Actually, our schedule matches pretty well to the planned end of the shuttle in 2010. We have our first demo flight of Falcon 9 with Dragon at the end of next year. And then we'll get 2 more demonstration flights, one in summer of 2009 and another at the end of 2009. And that third flight will actually culminate in the transfer of, I guess, demonstration cargo and the return of demonstration cargo back to Earth. Until we cannot, at this point, deliver real cargo, it has to be demonstration cargo, because otherwise we'd violate some sort of bar-based acquisition or something to that effect. So if that schedule remains true, or doesn't slip too much, then in 2010 we should be able to start delivering cargo. And then depending upon when the COTS option B gets exercised, which is what adds the escape tower, the life support system, the seats, all the crew-related stuff, plus the ability for the crew to take over in the event of an emergency. So depending upon when COTS B gets activated, we should be able to, I think, do take people to the space station. Well, probably, early 2011, something like that. It really depends on when things get going. Well, if Bigelow has his, puts up a workable private space station, obviously we'd love to take people there and back. So I think that would be super synergistic. We do have a Bigelow launch on the Falcon 9 manifest for launching, I think it's a 2/3 scale version or something that approximately that size of one of the inflatable space stations. So so irrespective of what happens with the full-scale version or how well that does, and whether he's able to sell sell people a space station or lease it or whatever, we do have one launch of Falcon 9 with Bigelow. So how many launches can Falcon 9 take before it has to be permanently retired? I think it's really hard to make an exact prediction. We really have to look at what condition it is in when it comes back. The engines, we're aiming for at least 25 full mission duty cycles before any refurbishment is required of significance, and ideally upwards of 100 cycles. So we'd like to get something like that out of the rest of the Falcon 9 as well. So sort of target at least 25, hopefully as many as 100. But it really, it's going to really depend, on what condition things come back in. And I think like a jet, we'll have a maintenance schedule. So there'll be some things that need to be replaced every flight, some things that need to be replaced every 5 flights, some every 10 flights, some that really are just never going to wear out, in any kind of reasonable time frame. And then we'll have an inspection schedule. So just like if a jet engine has a hot section inspection every certain number of hours, and you replace this component every certain number of hours, we'll have something similar for the rocket. So we want to try to overall just sort of drive things in the direction of the way that jet aircraft are operated. So I don't think a lot of it is get as good as that, but we at least want to try to push in that direction. I actually, I always have been fond of space, but, well, first of all, I grew up in South Africa, so, there's not really much space stuff happening there. And then I only got my citizenship like last year, and that was 5 years after I got my green card. So I've only actually been allowed legally to work in space for 5.5 years. I apologize for not getting that last 6 months in there, but that's literally I could only legally work in space for the last 5.5 years. It was just general theoretical and experimental physics. I was undergrad only. I actually originally was going to go out and do a PhD at Stanford in the material science and physics of high energy density capacitors. So actually very applied, almost really engineering. And that was for use in electric vehicles. So I think there's potential to do some very interesting things with, if you can drive the energy density of a capacitor up high enough, then it's really the ideal solution for electric vehicles. So they have a quasi-infinite cycle in calendar life and extremely high charge-discharge rate. Really, you'd be able to recharge your car faster than you can fill it with gasoline. So that would be, I think that's, if somebody can figure out the capacitors and good enough energy density, then that would really be the optimal solution for electric cars. Right?